All right, folks, these are the answers to this test on energy and work 2023, period 2. I will try to spell out how you know something is forces and energy, because I feel like that is what the questions people have been having. So a pendulum is swinging in this arc. The net, meaning total work done by gravity from point A to point D. And the point of this question is, so the answer is positive, because from A to C, gravity's doing positive work because it's speeding up. Or you can think about the force of gravity, and this is what's tricky, and the motion is tangent to the path, but a little bit of that green force is in the same direction as the pink vector, right? When we did like mg, let me get a different color. Some of it isn't mg cos, but some of it is mg sine. So since this is in the same direction of the pink vector, positive work, how do you know it's positive work? Part of the weight is in the direction of the velocity. Also, it is speeding up. It's gaining kinetic energy, and that is coming from gravity. From C to D, gravity's pulling, down, and the ball is going slightly up. So gravity's taking away energy from C to D, but since this is a shorter path, and because the ball still has kinetic energy, right? Since it's still got kinetic energy, gravity has to have done more positive work because it's going faster at D than it was at A. All right, so that was a lot of talking, but hopefully that makes sense, positive work. The net done by the string from point A to point C, that one is tricky, but a classic. If you look at the velocity of the pendulum, always tangent to the path, and the string is always pointing radially inward, right? That was the positive force when you're going in a vertical circle. These two vectors are always perpendicular. And so the work done by the string is the tension times the distance times the cosine of the angle, and that angle is always 90 degrees. That is not the angle of the pendulum. That's not this theta. It is the angle between the force, which is tension, and the motion, which is always perpendicular. So tension is always pointing towards the center. Velocity is always tangent to that. Okay, so that's a classic question that perpendicular forces don't do any work. It also should make sense that it's gravity that's speeding it up and slowing it down. The tension is just turning it, and turning it is not taking away kinetic energy, it's redirecting the velocity. Okay, those were tricky. Again, I think the conceptual questions are always what people find the most challenging, no question. All right, so we have 2 blocks, a 3 and a 2 kilogram block, and he puts the fan cart behind the block and they travel with a single object. So you can just pretend like this is a single 5 kilogram block. All right, so this says use work and energy, clearly not forces, to calculate the speeds. So speed will never be about equilibrium. Okay, the only thing that will ever potentially be forces is position, because equilibrium is a specific point. It is a location, right? So anyway, I realized that today, but speed is always, always, always energy because it's part of kinetic energy. And we're going from A to B, and we want to find the speed at B. Okay, this has friction. I'm not going to go through this because if you need to look this up, go look through your notes. But, sorry, hang on, let me slow down a little bit. So we're going from point A to point B. It says work. So I would suggest, even though it doesn't say, draw a force diagram. I would suggest you draw a force diagram so that you can think about which forces are doing work. So you have normal 3, normal 2, weight of 3, weight of 2. You have this 5 Newton force that's clearly an outside force putting energy into the system, and you have friction. Okay, so the green forces we don't care about. The normal is perpendicular to the motion, so just like we talked about with tension, it's not doing any work. It's not transferring any energy. Weight is not perpendicular to the motion. Part of weight is with the motion, but we're not going to calculate the work done by the weight because that work is accounted for when we do MGH. Basically, we're saying the Earth is in the system. This is really an internal force. We're just too lazy to draw the Earth and go, oh, I actually have 2 weights. Those are going to cancel. Okay, so it's just the orange forces that are doing work. So we're going to say TME at A plus the work done by the fan. I'm just going to say 5 Newton force plus the work done by friction equals TME at B. So one classic mistake is to, and I would make this myself, so that's why I'm warning you, is just to go, oh, to focus on either friction and go, oh yeah, that's taking energy away, and just include this. Or think about the fan because that's what you land on first. I have done that when I'm done doing answers to problems. So write yourself a note to make sure that you are including every single force that's changing the energy of the system. Okay. Then you have to decide where sea level is. So let's call that H equals 0. There's no spring, so that's nice. You don't have to, if you know there's no springs, you don't have to say 1/2 kx squared to make it 0. Sorry, that's an FG cosine theta. That is a really bad FG cosine theta. Okay, plus MGH plus 1/2 MV squared. Okay, so let's do a new color so we can see the line. Okay, so at the top, again, it's one aggregate 5 kilogram, 9.8, and the height is 0.342. That's your MGH. Nice. We're assuming it's starting from rest because otherwise we can't do the problem. Okay, and then the force of the fan is 5. The displacement is 1 meter. People are really tempted to say cosine of theta and go, I need a theta, cosine of 20. It is not cosine of 20. We want the angle between the 5 newtons and the motion or the velocity vector. These are pointing in the same direction, so this is cosine of 0. So the fan did 5 joules of work from A to B. Okay, for friction, I recommend you use your miscellaneous column because I tend to drop this distance D once I have tried to calculate friction here because then I've already got 2 things. So mu is 0.18. The normal on an incline is not mg, it's mg cosine theta. So friction is 3.315 newtons. Which is good that it's less than 5, right? Otherwise, we're taking away energy faster than we're getting it. So that's just friction times the distance, which is also 1 meter, because friction acts for the whole distance, times what is the angle between friction and the motion. That is 180. So that's times cos 180. So we got 1 term, second term, 3 terms, equals the TME at B. All right, so at B, I'm at sea level, so guess what? I can throw out MGH. But I better have velocity because that is the freaking question. So that is what we're looking for. All right. That's the setup. I'll try not to talk too much. That gives you, when you work out the math, it started with 16.758 joules of gravitational stored energy. The fan put in 5 more joules. Friction took away 3.315 joules. The reason these numbers are the same is because the distance was 1 meter, but that's not always true. Equals 2.5 VB squared, and you get a VB of 2.72 meters per second. Boom. All right. Then he puts the fan cart in front, and they travel as individual objects. So now we're going to look at what happens to the speed of each object at the bottom of the incline. So it's really 2 separate problems. So let's look at the block. So the block is TME at A plus this. I would just get in the habit of writing some of the work so you don't just stop at one force. Okay, and the block has only MGH. We've already talked about that. The block only has friction acting on it because we pulled them apart. Equals, and I'm going fast because we already kind of talked about this, at the bottom it only has kinetic energy. Okay, so let's plug in what we know. It is 2 times 9.8 times 0.342. Plus, we already know what friction is. It's the same thing, so don't make more work for yourself. 3.315 times 1 meter times cos 180 equals 1/2, be careful, we're only looking at the block, so it's 1/2 2 VB squared. All right, and then if you're comparing your work, I got 6.7032. Friction did the same amount of work because everything was the same. So you get VB is 1.841 meters per second. Check your work. I like this question a lot, and I would have liked to have asked, if I didn't have the pendulum logic, like explain why this answer makes sense. So let's look at that 1.841. That's less than 2.72. That makes sense because, oh, too bad, the block only got the thing that took energy away from it. So it clearly, when it hits the bottom, that's why I had to put it behind, because it's going. We're going to see it's going slower than the 3. But again, that should make sense that it is less because it got the raw end of the deal, because it just got friction, not the fan. Okay, so that's the block. And then if we look at the fan cart, we got TME at A plus potentially many works equals TME at B. And at point A, it is not moving, so it only has MGH. It lucked out, it got the fan, and at the bottom, it's at sea level, so it only has kinetic energy. So be careful with your mass. We're only looking at the fan cart. And the fan is still just going in the direction of motion, so that's cosine of 0 equals 1/2 3 V at B squared. Okay, so the fan cart started with more energy because it has more mass, and it got more energy because it got the fan in the luck of the draw. And so if you solve that for V of the fan cart, it is 3.168 meters per second. So again, check your work. 3.168 is bigger than the 2.72. And if you know weighted averages, one way to check your work is you could take the 1.841 and weight that by 2 kilograms of mass, plus 3.168 weighted by 3, and then divide it by 5, and you should get the average speed. So that's just like an interesting little side note if you like math and averages. Okay, and then this is the logic question. Was the total in experiment number 2 greater than or less than or equal to kinetic energy in experiment 1? All right, I know you know how to calculate this, so I'm going to do this on pause and then we'll check in. So in experiment number 1, there was a single object with a single speed. That's the amount of joules. In experiment number 2, you got to calculate it separately. 1/2 mv1 squared plus 1/2 m2v2 squared. But to rounding errors, you get this same amount of energy. Okay, so I don't remember how I pointed these. Maybe 3 points for calculating it, for understanding you had to do this as 2 separate terms. And then the explanation is, let's see, explain your answer. So the total is the same. Say this in your own words, but this is what I wrote. Both blocks start with the same initial energy as before, right? They both start at the same height. And the fan did the same amount of work as before. The friction did the same amount of work as before. So we didn't change the force or the distance for the fan or friction, right? We didn't increase friction or the fan or only have it act for a certain distance. So that you had the same initial energy and you had the same work done. So you're going to end up with the same final energy. It's just distributed, it is distributed differently, right? One of them has more speed than before because it got the fan, and one has less speed than before because it got the short end of the stick and got friction. Okay, so good logic question. Hopefully that felt good to you. All right, now we're going to do bungee jump problem. I'll let you read this on your own. Again, just to make sure that the bungee, there's going to be a twist to the bungee problem. In this case, the twist is there's 2 bungees, and they don't engage at the same time, which made it just a little bit annoying. I think is the point, but anyway, I'll pause and copy this, but pause this here if you need to read or write anything down. All right, so I said decide on your gravitational sea level and label on the diagram. I strongly recommend that you label point B. You don't have to do that. I'm going to do that because that's what my key has. So that's H equals 0. And then you might have decided that C was 0. You will get different TME than I will, but you'll get the same final answer. Okay, calculate the total mechanical energy based on your sea level. So this is where people have gotten stuck. There's only going to be one spot where you know the total mechanical energy. So if you want to kind of unlock your physics brain, just start by saying, all right, total mechanical energy, what do I know? It's all of this stuff, right? And so where do I know the height? I know the height at A, I know the height at C, I don't know the height at D, so that's not going to work because I don't know the height. Where do I know the speed? I know the speed at A because Clea drops over the bridge. I don't know the speed at B. I don't know the speed at C. Okay, and then where do I know let's double check, 1/2 kx squared. Oh, the bungee's not engaged there. That's awesome. I know it's not storing any energy there. So that's a hint that we're going to use A to find the total mechanical energy. So sometimes people have gotten stuck there. And we kind of just talked through why they only have MGH at point A, because they're not moving and the bungee is not engaged yet. So MGH is equal to, thank you for your patience, 87 times 9.8 times 3.7, or 3,155 joules. That is the energy in the system. No matter where we look, that is the energy. It's just distributed differently. Okay, and then, oh, well, this is not a surprise. This is forces. Draw a force diagram and calculate their equilibrium position relative to your sea level. So this is equilibrium, and so we're going to draw a force diagram. So we have weight, which is 87 times 9.8 And then, just like the escape room, there are 2 springs, but you can't just double it because they have different spring constants and they're stretched by different amounts. So this, this question is kind of testing attention to detail. Let me just finish the forces first, and then which one is stretched more? I don't want to waste your time. One of these is stretched more for sure, but it might have a weaker, wimpier K. So I don't actually know which of these 2 forces is bigger, but I know they're both pulling up. Okay, so that's your force diagram, and so we'll just do it here. By definite, equilibrium means the forces are balanced. Okay, so we're going to have K1 delta X1 going up plus K2 delta X2 going up minus mg going down equals 0. Okay, and then actually the other colors show up better. K1, now I'm going to be careful. This one's 480. That is stretched by, it engaged at 3.7. So that is stretched by yeah, oops. I had changed the problem. This is tricky, and I just want to try to visually show you that the first bungee engaged here, so it is stretched by, I'm calling this delta X. So the first bungee is stretched by 0.6 plus delta X. The second bungee is only stretched by delta X. Okay, that was tricky, a little bit annoying. Don't know that I would do that again, but okay, so it's a little bit tricky with the algebra, but you get 480 times 0.6 plus 480 times x plus 560 times x equals 853, and then I got 288 plus 1040x equals 853. So then 1040x equals 565. So x equals 0.543. Okay, which seems reasonable because that was 0.6, so another 0.543, kind of on the same order. Okay, so I want to make sure I answered the question. Equilibrium position relative to your sea level. So if this is sea level up here, what I solved for was delta x. So again, if this was clear on your test, that would give me, you would get full credit, like you did the physics right. What the question is technically asking is how far below sea level. So the actual distance is the 0.6 meters plus the 0.543. So they're like 1.143 meters below sea level. But again, if you had made it clear what you solved for, that's fine. Okay, that is sea level. And then find the Clea's speed as they pass through equilibrium. So again, speed is always kinetic energy. So we want to find the speed. I will clean this up. We want to find the speed here. So what we have here is we already found the TME at A, and we're looking for the speed at equilibrium. So we're clearly saying TME at A equals TME at D. Do not have enough room here to do that, but I want you to pay attention to what's tricky about this problem and use the diagrams on the test, ask for scrap paper, I think it can be human nature to be like, I got to start calculating the numbers, but you will, I think, save time in the long run if you set this up and go, all right, I need to set things up. So the bungee number 1 is stretched by 1.143 meters because it engaged first. Bungee number 2 was only stretched by 0.0543 meters. Most of the points on the test are, do you understand how many energy terms there are? Clearly, it's important to be accurate and understand what's going on if things aren't, super plug and chug. But I don't want you to stress out and think, oh my God, if, this is worth 20 points. So I don't know if that's clear or not. So we want to calculate Clea's speed as they pass through equilibrium. So I'm going to do this up here because I have no idea why that's not from there. Okay, so TME at A equals TME at equilibrium, which I think is D. We already found the TME at A was 3155 joules. Okay, so again, what I really, really care about and where most of the points in the rubric are is what kind of energy does Clea have at D? So let's just talk through that carefully. Clea is not at sea level, right? So this is the only time they would not have UG. So we have UG there. So we've got an MGH where H is below sea level. It's equilibrium, not turnaround. So they actually have the fastest speed. And again, a little bit annoying. I think on a different version of the test, they were stretched the same amount. I have no idea why. Sorry, this is too much talking, but some years kids are like, we have another test and we have another example test, and I give out so many tests that I got to put something different on the test, and then it comes out to be a little bit too much. Okay, so 3155 equals 87 times 9.8 times, they are 1.143 meters below sea level. So negative 1.143 plus 1/2 87 V squared, that's what we're looking for, plus 1/2 480 times 1.143 squared plus 1/2 560 times 0.543 squared. This was a doozy. So I can't remember where I paused the video, but you can pause this yourself and look through the numbers. A tricky thing is below sea level, make sure that's negative. Looking for speed. Each of these bungees was stretched by a different amount, and that is what you get when you finally solve for speed. All right, so that was the speed through equilibrium, and then lower turnaround location, and we are done. So turnaround means KE equals 0. So don't redo calculations that you've already done. So we know this. That's the same. And I'm just going to talk about this and then turn off the video and come back. We know that turnaround means that term is going to be 0. We're looking for how far below sea level we are, so that's going to be what we don't know. You can call it H if you want, or X. This is what's tricky. This is why you want to set sea level to be unstretched, because one of these springs is going to be easier to calculate. The other one, you can't set sea level to 2 different spots. So this is going to illustrate why that's, why we like that point. Okay, so let's go back and look at spring. Okay, so the green spring, whatever distance we're looking for, that is the stretch, right? We're looking for how far below sea level we are. That, because we set that to sea level, that is the stretch of the spring. So I'm going to call that X as well. But spring number 2 is not stretched by X. Spring number 2 is stretched by X minus 0.6, right? If this is 0.6, then this, whatever this stretch, because that's not the, like, X is some turnaround point down here. Okay, and so this spring is stretched by X. This string, this bungee is stretched by X minus 0.6. It's not stretched as much. So whatever X is, this stretch has to be less than that by 0.6. That's why we want to set sea level to the same unstretched. Otherwise, we have to do this annoying correction. Okay, folks, I made a mistake. I said X minus 6 instead of X minus 0.6. And it took me forever to find the mistake. I kept getting no real solution. So, again, this problem is way, I would not assign this again. It's unnecessarily complex. I would give you 2 bungees, but I would have both of these X's be the same. But since I already Xeroxed the test, I'm going to finish this up for you all. So, person has 3155 joules at the beginning. This turns into 852.6 X. No kinetic energy because it's the turnaround point. Plus 240 X squared. That's still good. And I dropped the 2 on that too. Plus 280 times X squared minus 1.2 X plus 0.36, right? So we're just expanding this here. And then you want to combine like terms. You know, you can speed through this if you want, but just in case people want to find where their mistake is. So this is 280 X squared minus 336 X plus 100.8. That's what this distributes to. And then you have, I just combine like terms. So and then you get out your quad solver. This is A, this is B, this is C. And I get X equals 1.98 and negative 2.97. We were solving for X, and we know we're below sea level, so we want to pick the negative answer. Okay, that was distance below sea level. So again, I think that's what the question asked. That was relative. If it said relative to the bridge, then we'd have to add the 3.7 below the bridge, right? So we should add the 3.7 to that value, to the magnitude of that value to get total distance below the bridge. Okay, so that was really long and tedious. So again, sometimes physics is just that way, but that is what it is, and hopefully that went okay for you. All right, see you later.